Welcome to Statistics Made Easy. This session is dedicated to understanding the regression output you receive after running a linear regression model in Stata. From our practical sessions, you may remember that you can implement a linear regression model, in this case an ordinary least squares regression, using the regress command. It includes our dependent variable, which in our case is the amount of ice cream consumed, along with a set of independent variables such as the temperature and whether our customer is a child, and our control variables like the income of our customers and the location of our ice cream parlor. Once you run this regression command, you receive this output, which is divided into two parts. The upper part provides some general statistics on your model, and the lower part provides more specific estimation outputs on your covariates. That is your list of explanatory variables. Let's start by looking at some of the key values in the upper half of the output. First, you see the number of observations in your model. This is an important check always, especially if you estimate different models with different number of covariates or explanatory variables. Your first model typically only includes your control variables, and the next model then adds your explanatory or independent variables for which you have hypotheses. To be able to compare the model statistics and the coefficients, you want to ensure that you're estimating your models on the same sample throughout. This can often vary. For example, if you have missing values in some variables. And to set your sample at the beginning, please check out my video on setting the sample, which gives you further information about this issue. Next, we have our F statistics. The F statistics test the null hypothesis that all the regression coefficients in our model, which you see here in this output, are equal to 0. This would be, so to say, our worst case scenario. Imagine that all our potential explanations for the outcome do not hold. Our F value, luckily in this case, is very low, so we can reject this null hypothesis. This means that at least one of our coefficients is not equal to 0. That is either larger or smaller than 0. The next value of interest is the R-squared value, which is the percentage of variance explained by all the covariates. In our case, we can explain 84% of the variance in our dependent variable with our current set of variables. This is a very high value. In the social sciences, you will typically find values between 20 to 40%. And you should also note that as you add more explanatory variables or covariates to your model, the R-squared will automatically increase no matter whether these independent variables and control variables actually add any explanatory power to your model. As a correction for this problem, we also have the adjusted R-squared value. And this value will not increase as much with an increasing number of covariates. And this may then be a better reflection of your explanatory power, actually. Let's now move on to the lower half of the output. Here you see our estimations for our explanatory variables that we included in the model. Let's first look at the columns in this output. We have, first of all, our variable names, followed by our coefficients. The coefficients, if you remember from our introduction to multivariate statistics, are the effect sizes or the slopes of your regression lines. Next, we have the standard arrow. And if you divide the coefficient by the standard arrow, you get the t-value. Higher t-values are typically associated with higher statistical significance. But to be sure, we want to check this in our t-value distribution table, and then we can see the corresponding p-value, which we get automatically here in our output as well. The p-value is typically used to interpret the statistical significance of a relationship. And also you see this quite frequently in hypothesis testing, in formal hypothesis testing. The interpretation is that if the p-value is below a certain threshold that you define, then you can reject the null hypothesis that the coefficient is equal to 0. In this regard, the interpretation is very similar to the F statistics, which test that all the coefficients are equal to 0. And in this case, the p-value tests that this specific coefficient is equal to 0. And a word on the cutoffs. Often you will find in papers cutoffs at the 5% level or the 10% level of statistical significance. But in reality, you should probably adjust the interpretation based on the sample size. As your sample becomes larger, typically more variables will become statistically significant. And in this case, you should more transition towards interpreting the effect size rather than just looking at the p-value. And you should also have a lower threshold for interpreting significance if you have a large sample compared to a very small sample. Now, let's look at the specific interpretation of this linear regression output. The general way of interpreting the output is the same for all the independent variables. For temperature, it would be that a 1 unit increase in temperature, that is an increase by 1 degree Celsius, increases on average your dependent variable by 2.2 units. In this case, let's assume it's grams of ice cream, holding the other covariates in your model constant. So the coefficient is really the unit change in your dependent variable triggered by an increase in your independent variable. In our case, this relationship is also statistically significant. For the variable child, you would argue that the ice cream consumption for children is on average 9.5 grams higher than for adults, because a 1 unit increase in this variable is the change from adults to children. So whenever you interpret the 1 unit increase, you hold the other covariates in your model automatically constant and interpret the unit change. And depends in which unit your dependent variable is measured. If it is grams of ice cream or dollars or happiness, that then depends and affects your interpretation. In case you're interested in how a 1 unit increase affects your dependent variable at different levels, then you can use the margins command in Stata to set these levels. Well, check out my video on moderation analyses to see this in practice and how we can look at the effect of an independent variable on a dependent variable at different levels of the independent and the moderating variable. Thank you very much for joining this session. I hope you find it useful, and I look forward to seeing you in our next session.